Are you confused about logical negations and contrapositives in your proof-oriented math course? Maybe you're in real analysis and you're really confused about all those sups and infs everywhere. If so, then this video may be what you've been waiting for. This is Study Help for Baby Rudin, Part 1.3. We're going to study sups and infs, also called lubs and glubs, including trying to understand this example, the fact that the sup of the outputs of the cosine function as the inputs n range over the natural numbers equals 1. This is a non-trivial example. Baby Rudin is one of the premier texts in real analysis, but it's a tough book, and I want to help you through it. That's the purpose of these videos, and that's also the purpose of my blog posts at my blog infinityisreallybig.com. But even if you're not using Baby Rudin, or even taking real analysis, you can still get benefit from these videos and blog posts. The highlights of this video include a Mathematica animation helping you to believe that the supremum of the set of the outputs of the cosine function as the inputs range over the set of natural numbers is equal to 1. Yet another Mathematica animation will help us understand the proof of why the supremum of the set of those outputs equals 1. Let's now get into the mathematical details of sups and infs that you can find in Baby Rudin or any other real analysis textbook for that matter. We are given a totally ordered set S. Most typically we think of S as being the real number line, and we imagine it as being a number line. There's a total order on it. If A is to the left of B on such a line, then we think of A as being less than B. We are also given a subset capital E of S, which is assumed to be bounded above. This means there exists an element of S which is greater than or equal to every element of E. The question we want to answer is, does E have a least upper bound, or lub? We're usually going to call this supremum or sup. And is this least upper bound or sup in S? The short answer to this question is, it depends. In fact, it depends on what S and E are. Now let's be more precise. Here's the official definition of the supremum of a set. We are again assuming S is a totally ordered set and E is a subset of S, which is bounded above. An element beta in S is the supremum of E, written beta equals sup of E, if, number 1, beta is an upper bound of E, so x is less than or equal to beta for all x in E, and, number 2, any element of S that is less than beta is not an upper bound of E. In other words, if gamma is less than beta, that implies there's some element x in E such that gamma is less than x. Another way to say this is that beta is less than or equal to any other upper bound of E. Beta is the least upper bound of E, but more often we're going to call it the sup of E. This is now a good point to just take a minute and talk about the logical concepts that I talk about in my article at infinityisreallybig.com, logical negation and logical contrapositive. Beta is an upper bound of E means that the following is true. X being in E implies that x is less than or equal to beta. You can also say that in this way. For all x in E, we have x less than or equal to beta. The upside down A is called the universal quantifier. Think of it as shorthand for the phrase for all. The logical negation of this definition allows us to define what it means for beta to not be an upper bound of E. It means that there exists an x in E such that x is greater than beta. The universal quantifier, the upside down A, that stands for all, has been changed to an existential quantifier, the backwards E, which stands for there exists, and the less than or equal to sign has been changed to its opposite, the greater than sign. This should make intuitive sense. Draw pictures to help you see it. We will soon be considering examples. The logical contrapositive of an implication is a new implication created using logical negation that is equivalent to the original implication. It means the same thing. For the definition of beta being the least upper bound of E, we have the following being true. Gamma being less than beta implies that there exists an x in E such that gamma is less than x. In other words, gamma is not an upper bound of E. The logical contrapositive of this implication takes the premise and the conclusion of the original implication, switches them around with respect to the implication, and negates them. Its meaning is equivalent to the original implication. In this case, what that implies is that beta is the least upper bound of E if x being less than or equal to gamma for all x in E implies that beta is less than or equal to gamma. In other words, if gamma is an upper bound of E, then beta is less than or equal to gamma. Beta is the least upper bound of E. Now let's consider some examples. For example 1, we let E be the closed interval from A to B. In other words, E is the set of all x in R, the real numbers, such that A is less than or equal to x is less than or equal to b. We include both A and B in the interval. Then the supremum of E is equal to b. Why? Well, clearly to start with, b is an upper bound of E. By definition of E, every element x in E is less than or equal to b. Secondly, if gamma is another upper bound of E, meaning gamma is greater than or equal to every element of E, then b itself would have to be less than or equal to gamma because b is in E. In summary, then, the sup of a closed and bounded interval from A to B is the right endpoint, the largest value in that interval. Running this Mathematica code that you see here will help me understand what's going on. When I run it, I see a blue interval that is a closed interval from A equals 2 to B equals 5. I also see a red dot labeled beta equals 5.25. That's not the sup of E because it's not the right endpoint of E. It is an upper bound of E, but it's not the least upper bound. If I change beta to be less than 5, then it's no longer even an upper bound of E. Only when beta equals 5 exactly do I get the sup, do I get the number that is an upper bound of E and also the least upper bound of E. Beta is the sup of E. In fact, you could also call it the lub of E. Lub spelled L-U-B for least upper bound. This also hints at a related dual concept for sets that are bounded below, the concept of a greatest lower bound, or glub, which we are usually going to call infimum or inf. If I decrease beta to equal the left endpoint, the lowest value in E, which is 2 exactly, that is the inf of E, the greatest lower bound. Any number less than 2 is a lower bound for E, but not the greatest lower bound. Any number bigger than 2 is no longer a lower bound of E. 2 is in fact the greatest lower bound. It is the inf of E. The concepts of sups and infs gets tougher when the interval under consideration is an open interval, which we consider in example 2. Let E be the open interval from A to B, not including the endpoints. This is the set of all x in R with A less than x less than b. This set is certainly bounded above and bounded below, but it has no largest element and it has no smallest element. However, the sup and inf do exist. The sup of E is the right endpoint B, and the inf of E is the left endpoint A. The sup and the inf are not in the interval, but they do exist as real numbers. Why? Well, the first reason is still clear. B is still clearly an upper bound of E. On the other hand, the second argument is harder. If gamma is another upper bound of E, is B less than or equal to gamma? The argument is not as straightforward this time because B is not an element of E. Instead, we use the contrapositive. Suppose that gamma is less than B. In the special case where gamma happens to be less than or equal to A as well, we can say that the average of the two endpoints, A plus B over 2, is an element of E with the property that gamma is less than x, and we would be done. In the other case, when A is less than gamma, we have no guarantee that A plus B over 2 is bigger than gamma. But that's not a problem. Let x be the average of gamma and b, gamma plus b over 2. That's still an element of E, and now this has the property that gamma is less than x. In either case, we have just shown that any number less than b is not an upper bound of E. Therefore, b must be the least upper bound, supremum, of E. An analogous argument shows that the left endpoint, A, is the greatest lower bound, or infimum, of E. It's worth emphasizing one more time. The sup of the open interval from A to B is the right endpoint B, which is not in the open interval from A to B, and the inf of the open interval from A to B is the left endpoint A, which is not in the open interval from A to B. Once again, I have Mathematica code that I can run to illustrate this. Now you see the open interval from 2 to 5, indicated by the open circles at 2 and at 5. Those individual points are not included. 5.25, 5.31, those are all upper bounds of E, but not least upper bounds. Things like 4.87 or 4.82 are no longer upper bounds. 5 is indeed the least upper bound, the sup. It's an upper bound of everything in E, and anything less than 5 is no longer an upper bound of E. On the other side of the interval, 2 is indeed the greatest lower bound. It is the inf. Anything less than 2 is a lower bound, but not the greatest lower bound. Anything bigger than 2 is no longer a lower bound of E. The next two examples are related, so I'm calling them examples 3a and 3b. These are both infinite sets, but they are discrete infinite sets, countably infinite if you know what that means. Let E be the set of all numbers of the form 1 minus 1 over n, where n ranges over the natural numbers. In other words, n is first 1, then 2, then 3, then 4, etc. So the elements of E include 1 minus 1, which is 0, 1 minus 1 half, which is 1 half, 1 minus 1 third, which is 2 thirds, 1 minus 1 fourth, which is 3 fourths, etc. And let F be E union with 1 point, the number 1. Then we can say that the sup of E equals the sup of F equals 1, and the inf of E equals the inf of F equals 0. You may want to pause the video and see if you can prove these things. Notice that 0 is in both E and F, while 1 is in F but not in E. Rather than doing a proof, I'm just going to run Mathematica code to illustrate this. So the blue dots that you see are the elements of E. 1 minus 1 is 0, 1 minus 1 half is 0.5, 1 minus 1 third is 2 thirds, 1 minus 1 fourth is 3 fourths, etc. The number 1 is not an element of E, but it is an element of F. You could pretend it's not a blue dot when you're thinking about E, and you could pretend it is a blue dot when you're thinking about F. Any number beta greater than 1 is an upper bound of E, but not the least upper bound. Any number less than 1 is no longer an upper bound of E, no matter how close to 1 it is. Only 1 for both E and F is the least upper bound. On the other hand, 0 is pretty clearly the inf of E. It is the greatest lower bound. More examples of similar difficulty can be found at my blog, infinityisreallybig.com, at my third blog post about baby Rudin. But now we're on to our main example. Let E be the set of outputs of the cosine function as the inputs n range over the natural numbers. So this includes cosine of 1, cosine of 2, cosine of 3, cosine of 4, etc. Then our claim is that the sup of E equals 1 and the inf of E equals negative 1. This is by no means obvious. After all, because of the oscillation in the cosine function, the limit as n goes to infinity of cosine of n does not even exist. Moreover, cosine of n never equals plus or minus 1 for all natural numbers n. That's because no natural number can be a multiple of pi. Even more amazingly, cosine of n is an irrational number for n equals 1, 2, 3, 4, etc. Before we look at the proof, let's use Mathematica to help us believe that 1 is the sup and negative 1 is the inf. Certainly, 1 is an upper bound of the set of outputs and negative 1 is a lower bound. But the question is 1 the least upper bound and is negative 1 the greatest lower bound? 1 will be the least upper bound of E if any number even slightly less than 1 is no longer an upper bound of E, and negative 1 will be the greatest lower bound of E if any number even slightly larger than negative 1 is no longer a lower bound of E. Using Mathematica, we see that cosine of 1 is about 0.54, cosine of 2 is about negative 0.42, cosine of 3 is close to negative 1, about negative 0.99, cosine of 4 is about negative 0.65, cosine of 5 is about 0.28, cosine of 6 is about 0.96, somewhat close to 1. The question is, as I keep increasing n, can I eventually come across values of the cosine function that are arbitrarily close to 1 and arbitrarily close to negative 1? Given any tolerance epsilon, no matter how small, say for example 10 to the negative 4 power, 0.0001, can I make the value of the cosine function be within that distance of 1 and negative 1 by taking little n sufficiently large? Let's continue increasing the value of n and just see what happens. When n is 7, I get 0.75. When n is 8, I get negative 0.15, etc. Continue, keep going, letting n increase. Do I ever get really close to negative 1 and 1? Well, there is an output. When n is 22, that's very close to negative 1. Cosine of 22 is about negative 0.99996. That is 0.00004 units away from negative 1, within 10 to the negative 4, for example. Continuing, letting n be 23, 24, etc., do I ever really get close to positive 1? There's a number pretty close to positive 1, within 0.01. I am only letting n go up to 30 here. Let's see if it gets closer to positive 1. No, it doesn't. However, if I go higher, in particular if I go up to n equals 44, it does get really close to 1, though not technically within 10 to the negative 4, but very, very close to that. Let's now look at a graphical display to help us understand what we just observed visually. When I run this code, I see a graph of the cosine function. I also see two red dots to start off with when n equals 1. This is the value of cosine of 1. It's slightly above 0.5. It's on the graph of the cosine function. I'm also labeling it on the y-axis. As I let n increase, I can see the values of the cosine function as n increases from 1 to 2 to 3 to 4, etc. We can see the values kind of densely filling in the interval from negative 1. When n is 22, that was the case where we saw the output was very close to negative 1. When n is 25, the output is very close to positive 1. And finally, when n is 44, the output is really close to positive 1. Given a small number epsilon greater than 0, is it possible to find a value of n so that cosine of n is bigger than 1 minus epsilon without just doing trial and error? Yes, this line right here is essentially a little program that I just wrote to help me do that. I'm setting epsilon equal to, for example, 0.1, but I'll also set it equal to smaller numbers. I'm setting n equal to 1, and then I'm creating a while loop. What is this while loop doing? While the value of cosine of n is less than 1 minus epsilon, not greater, I keep incrementing n up by 1. So when n is 1, I plug that in there, I get cosine of 1, which is less than 1 minus epsilon, so n gets incremented up by 1 to 2. I calculate cosine of 2. That is also less than 1 minus epsilon, so I increment n up by 1 to 3. And you keep going until this condition is not true. When that happens, you are at the value of n where in fact cosine of n is greater than 1 minus epsilon for that given epsilon. In this case, n equals 6 will do it. And indeed, we can confirm that cosine of 6 is about 0.96. That is within 0.1 units of 1. Next, let's try decreasing epsilon to 0.01 and see what happens. We get n equal to 25. We saw that before. That's within 0.01 of 1. Making epsilon equal to 0.001, we get n equal 44. That is within 0.001 of 1. Let's go ahead and be extreme with the next one and add 6 more zeros. So I'm at epsilon equals 10 to the negative 9 power now. The code runs and gives me n equals 103,993. I plug that into the cosine function, approximate it. I can see I'm within 0.000000001 of 1. While all that numerical evidence is great, it's only suggestive of the fact that the supremum of the set of outputs of the cosine function as n ranges over the positive integers is 1. It's not a mathematical proof. How do you know that, for example, if epsilon were 10 to the negative million power, that you would never be able to find a value of n, so that cosine of n is within epsilon of 1? Therefore, we need a mathematical proof. We need to know that we can find n no matter how small epsilon is. So we start our proof by saying, let epsilon greater than 0 be given. It's a positive number that can be arbitrarily small. Next, choose a positive number delta so small that 1 minus cosine of x is less than the given epsilon if the absolute value of x is less than delta. In other words, if x is within delta units of 0. This is equivalent to cosine of x being bigger than 1 minus epsilon if the absolute value of x is less than delta. Why can this be done? It can be done because of the continuity of the cosine function at x equals 0, plus the fact that cosine of 0 is 1. We can make cosine of x as close as we like to 1 by taking x sufficiently close to 0. In fact, for this example, we can even choose delta in a nice and programmable way. As long as epsilon is less than or equal to 2, we can choose delta using the inverse cosine or arc cosine function. In particular, we can let delta of epsilon be the arc cosine of 1 minus epsilon. Then the cosine of delta would be equal to 1 minus epsilon, and our inequalities would be true as well. If we plot this function, we see that delta increases pretty rapidly as epsilon increases away from 0. That's because the graph of the cosine function at x equals 0 has a horizontal tangent. The practical consequence of this is that when epsilon is really, really small, we can actually get away with a relatively large delta and the proof will still work. Next, by something called the Archimedean property, even when delta is really, really small, we can choose a positive integer capital N such that 1 over capital N is less than delta over 2 pi, which is equivalent to saying 2 pi over capital N is less than delta. In fact, we can use the ceiling function, which rounds up to the smallest integer greater than a given number, to define capital N as a function of delta to be the ceiling of 2 pi over delta, and we can graph that. Here we do see that as delta gets smaller and smaller, n gets larger and larger, as you would expect. For purposes of visualization, it will now be beneficial to view n as an angle in radians, and define theta sub n to be the equivalent angle in the interval from 0 to 2 pi that includes 0 as the left endpoint but does not include 2 pi as the right endpoint. In other words, theta sub n can be found by taking n and modding by 2 pi. In Mathematica, we can use the function mod n comma 2 pi to do it, and here are some representative values for the values n equals 14, n equals 100, and n equals 1000. Numerically, we get 1.43, 5.75, and 0.97 as the equivalent angles in the interval from 0 to 2 pi in radians. If we plot this function, we get a piecewise continuous function that has jump discontinuities at multiples of 2 pi, and you can see the output is always in the interval from 0 to 2 pi. Now partition the interval from 0 to 2 pi into capital N intervals of length 2 pi over capital N. Remember that 2 pi over capital N is less than delta. So the first interval goes from 0 to 2 pi over n, the second from 2 pi over n to 4 pi over n, the third from 4 pi over n to 6 pi over n, etc. The last interval will go from 2 times n minus 1 times pi over capital N to 2 pi. Before we consider the n plus 1 values of theta that you see here, let's use this code in Mathematica with the table command to illustrate where the endpoints of these intervals will be when capital N is 14. If capital N is 14, they each have length 2 pi over 14, which is pi over 7, which is evidently approximately 0.448799. You can see that these would be the endpoints of those intervals. This code will once again use the table command to compute the theta values, theta 1, theta 2 through theta n plus 1. When n is 14, we get these 15 points. We can count them to double check that there are 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. These are the values theta 1 through theta 15, all between 0 and 2 pi. I have taken the values 1 through n plus 1, 1 through 15, and modded by 2 pi. Since we have n intervals and n plus 1 points, for example, 14 intervals and 15 points, the pigeonhole principle would say that at least one of these intervals, say the one you see here, contains at least 2 of the points, say theta sub a and theta sub b, where, without loss of generality, we can assume a is less than b. This code will illustrate this in the case where capital N is 14 and therefore capital N plus 1 is 15. We see a number line with blue dots. Those blue dots are the values of the endpoints, and we see one red dot at the value of theta 1. I can let n increase to see theta 2, then theta 3, etc. Once we get past n equals 6 to n equals 7, now we are modding by 2 pi. Theta sub 7 is pretty close to theta sub 1, but not in the same interval. Theta sub 8 is equally close to theta sub 2, but not in the same interval. Theta sub 9, you can see, is equally close to theta sub 3, but also in the same interval. That would be an example of an a and b we can use. A is 3 and b is 9. Are there any others? Yes. Theta 10 is in the same interval as theta 4, and theta 14 is in the same interval as theta 8. We're almost done. Now let d be the distance between theta sub b and theta sub a, which you can check will be the minimum of the values b minus a mod 2 pi and a minus b mod 2 pi, and let n equal b minus a. The claim will be that cosine of n is within epsilon of 1. Just to illustrate, in the case where a equals 3 and b equals 9, the distance d between theta sub b and theta sub a will be 3 minus 9, or negative 6 mod 2 pi, which is about 0.283. And then you can check that cosine of b minus a, which is cosine of 6, is approximately 0.96017 within 0.1 of 1. In terms of a rigorous argument, when n is b minus a, which is a natural number, we can say that the absolute value of theta sub n, the distance between theta sub n and 0, is the same as d, which is less than 2 pi over n, which is less than delta. Therefore, by how we chose our delta at the beginning of the proof, we can say that cosine of n, which is cosine of theta sub n because n and theta sub n represent equivalent angles, is greater than 1 minus epsilon, where epsilon was our given positive number that could be arbitrarily small. This code will visualize what's going on in terms of the unit circle when n is 14, which, by the way, is based on epsilon equal to 0.1 and delta equal to about 0.451. If I run this code, I see the animation that I showed you near the beginning of this video. We see the unit circle. We see a vertical green line whose first coordinate is at 1 minus epsilon, in this case 0.9. We see two red dots, one on the unit circle, whose coordinates are cosine of 1 comma sine of 1, and one on the horizontal axis, whose first coordinate is cosine of 1. I let n increase, and I do see that once I get to n equals 6, I am within epsilon of 1. The value of cosine of 6 is greater than 1 minus 0.1, greater than 0.9. And that's the end of this video. Thanks for watching.